What we're going to look at now is how we can adjust that astable Schmitt trigger oscillator to make a monostable oscillator or a monostable multivibrator. So let's give a clearer definition of what we mean by monostable. So monostable, of course, means that we have one stable state. And so it can remain in this stable state indefinitely until it gets disturbed. So it can remain indefinitely until disturbed or until it sees some sort of external excitation. And so in this case, what we're going to see is a trigger pulse can cause it to change states to some quasi-stable state. So trigger pulse can make it change to quasi-stable state. And so quasi being somewhat partially, so it's kind of stable. And after some time, it's going to decay back to the stable state. So it's here for a definite time. Then it's going to return to the one stable state. And so another name for this monostable multivibrator is a one-shot. And so that's because it's going to just have one sort of response to a disturbance, and then it's going to return to the stable state. So let's take a look at what this circuit looks like. So you can notice that the core of this circuit looks the same as what we saw for our astable Schmitt trigger oscillator, but we've added a few components. So I want to circle those and call those out explicitly. So over here on the left, we have a clamping diode D1. And so what we're going to see in the plots here in a little bit is this clamping diode is basically setting the maximum positive voltage of our capacitor at the forward bias voltage of D1, which we're going to call just a generic V gamma, a cut-in voltage. We also have two Zener diodes over here back to back connected to our output, and what this is going to do is this is going to set our saturated output values. So this is something that we could also do when we were looking at our Schmitt trigger circuits. We just didn't discuss that, but this is another way to set our desired saturated outputs. And then finally, this part down here where we have this V input is our trigger circuit. So this is how we're going to send an input pulse to this oscillator to make it leave its stable state momentarily. And so again, we see that the core of it, though, everything that's not circled essentially is the same as we saw for our astable Schmitt trigger oscillator. So a couple notes before we sort of dive into what the analysis is going to look like. So we can see that our stable state is going to be our output high. So stable state, our output is high. And as we said, in that output, with our output high, our Vx is going to be limited by D1, our clamping diode that was over here on the left of the circuit. And as we're going to see here in a little bit in the plots, our input voltage Vi is going to be a negative going pulse. So in the textbook, they have a negative step voltage, but I think it actually makes more sense in terms of having a negative going pulse. There are some issues we need to be concerned about in terms of timing, but we'll address those as we look at sort of the overall circuit. So one other thing before we start looking at some plots is we can also talk about the saturated outputs based on this DZ1 and DZ2. So let's look at those a little closer. So our saturated outputs, and again, just to write that out explicitly, we have these Zener diodes that are setting those values. And so as we can see, for instance, if we have an output high state, our DZ1 is going to be forward biased and our Z2 is going to be reverse biased. So we're going to have our forward voltage from DC1 and our Zener voltage of DZ2. So in that sense, we're going to say our VP is set at V gamma 1, the cut-in voltage of that first Zener diode, plus VZ2, the Zener voltage of our second diode. And so keep in mind, cut-in voltages typically on the order of less than a volt or around a volt, depending on what diode you're dealing with, whereas Zener voltages can be anywhere from tens of volts to hundreds of volts, again, depending on your particular diode. So this gives us a lot of design flexibility. Our negative value is going to be sort of just the opposite. Our D1 is going to be reverse biased and D2 forward biased. So we're going to have negative VZ1, which is a Zener voltage of that top diode, plus the cut-in voltage V gamma 2 of our bottom diode. And so going forward with this analysis, we're just going to focus on VP and negative VP, but sort of underneath that, know that that's set by those two Zener diodes. Okay, so now what we want to do is we want to sort of plot three things. We're going to plot our input voltage, our voltage V sub x, and our voltage V naught. And so let me come back up here and note as well that I've also labeled this differently from what we saw in the previous video. So now I've labeled this V sub y. So you'll notice I've labeled a couple of things on this plot already. I've got the times lined up, so I've got time 0, I've got time t, and time t primed. We're going to come back to some of these sort of other values. You see I've got VP and minus VP as we just discussed, and we'll come back and we'll define this and see why that's important here in a little bit. So let's take a look at our input voltage on our triggering circuit, because that's ultimately what's going to be setting everything off. So we say that our input, so let me change colors here. We say that our input voltage is going to be high, and therefore during this time, our diode D2 down here is going to be reverse biased, so it's going to be off, and this is essentially going to be isolated from our oscillator circuit. And so in that case, let's go ahead and say, let me go ahead and say this next part before we consider our triggering event. So typically that resistor R3 that's part of our triggering circuit, we want to choose that to be much larger than our R1 so that it doesn't affect that voltage divider network. So it doesn't affect our voltage divider. And so when that diode is reverse biased, that D2, it shouldn't be an issue, but for that brief time when it's forward biased, we don't want it affecting that voltage. So with that in mind, we can approximate our Vy as saying that that's approximately the same voltage divider we saw for our astable configuration, R1 divided by R1 plus R2 times Vp. And so we didn't write that out explicitly because before we had just assumed that R1 is equal to R2, but scrolling up here we can see this is the voltage divider with our V out to create our Vn, or our Vy here. Okay, so we get that, and to simplify things, I'm going to call this beta Vp, just so we're not having to write out this R1 divided by R1 plus R2 each time. So I'm going to call this equation 1. Okay, so now let's come back up here and consider what happens if we have a negative pulse on our input. So let's say we have this going down, so not necessarily negative, but negative going. So it goes low enough so that D2 becomes forward bias. And so let's say it just comes back up, and then from here on out, it's just going to stay positive. So again, we just need a sort of pulse. We don't need that to be maintained as it has in the book. But, so let me label here, we have, in this case, D2 is reverse biased, but down here, we have D2 is going to be forward biased. And so we can consider that by looking at our Vy, sort of in our stable state. We see it's beta, which is a positive number, times our positive Vp. So beta is positive, or rather, V sub y is positive. So coming back to our circuit, if our V sub y is positive and we drop this input voltage, that's going to be forward biasing this diode. So when that diode gets forward biased, it's actually going to pull this voltage down. So we're going to have some voltage drop across that diode, which is going to decrease Vy low enough such that it comes lower than this Vx, which I've forgot to label. So this voltage across our capacitor here is V sub x. And so of course that's going to cause our output state to switch. And so let's come down here and put some of that in writing real quick. So we have this negative step on the input, and I'm going to say step slash pulse on our input, and so that causes D2 to be forward biased, and so ultimately that's going to pull our voltage Vy down, and it's going to pull voltage Vy below our other voltage into our comparator Vx. And so what that means, based on sort of our basic comparator, is that our output is going to switch states to low. So our output switches low, which is negative Vp, and remember, ultimately that's going to be based on those two Zener diodes that are connected to the output. So let's come up here and let's sort of do our output plot. So we know that our output was high initially. We said that's our stable state. As soon as we see this negative going pulse, we said it's going to switch low, and now we're going to be at this low state. So we're just going to draw a little bit there during that pulse. So now as soon as that output voltage is low though, we're going to have to update this equation 1 for a new V gamma, because our Vp is no longer our output voltage. So this value is now negative Vp. So coming here, we can say now we have our Vy is equal to, again approximately because we have the R3, R1 over R1 plus R2 times a negative Vp. And so we can say this is equal to negative beta times Vp. And so let's call this equation 2. Okay, so now that this Vy is negative, let's come back up to the circuit for a second. And so let me erase some of this highlighting here. And so what we're saying is that this value of Vy has just changed to be negative. And so even if this pulse is still staying negative, we notice that our diode D2 is going to be reverse biased and is going to be disconnected, is going to sort of isolate our trigger circuit from the rest of our oscillator. Of course, especially if we wait long enough for this Vi pulse over here on the left to be increasing back from that negative pulse, then definitely our diode D2 is going to be reverse biased. So basically, our diode D2 becomes reverse biased and that becomes disconnected. What we're going to have then is our negative step change in our V0 is then going to be causing this capacitor to charge up. Charge up, discharge really depends on perspective, but basically if this voltage here is switching from Vp to negative Vp, this capacitor voltage was sitting at V gamma in the high state. Now it's going to be charging towards a final value of negative Vp. So let's that was all a qualitative look. Let's come put that into words and then adjust our plots. So first let's adjust this value here. So we can say that this is clamped at V gamma before our switching. So let me add in that this is V gamma of diode D1. And let's come back down here and say this causes, so because of this we have D2 becomes reverse biased. And that disconnects our trigger circuit from the oscillator circuit. So now we come back up here and we say, well, we had this negative step change in our output, this bottom plot, and so what that's going to cause is our Vx to decrease exponentially towards that negative Vp. So this step change in output is going to lead to Vx decreasing exponentially towards negative Vp with a time constant tau equals Rx Cx. So that's the same as we've seen before, just because again, that's sort of the path connecting our capacitor and our output, which is our either high or low state. Okay, so we come down here and we say, well, this is going to be discharging. So as long as that is low, this is going to be discharging towards a negative Vp, but we have this beta, which is less than 1, because remember this is R1 over R1 plus R2, this beta term. So before it's able to get to Vp, we're going to have it passing the Vy, because this is our, see, this whole value here is our Vy when our output is low. So when our Vx drops below that, then the output of our comparator is going to change back high. So let's come put that into words, and then I'll try to write that a little cleaner in the plot here. Okay, so what we have, change back to this, is we can say when our Vx drops below Vy, and so this is the Vy from 2, so this is equal to negative beta Vp, because our output is in the low state. What we have is our output switches high. And so of course the high value of our output is going to be Vp, ultimately dependent on those two Zener diodes. And then what happens is our capacitor is then exponentially increasing towards Vp. And so it's going to have that same time constant tau that we wrote above. So the tau is still just going to be Rx Cx. But remember we had that D1 in parallel. So sort of as a side note here, we can say Vx equals V gamma of D1. Basically when that diode D1 becomes forward biased, our Vx voltage gets clamped at V gamma. So let's come up here to our plots and sort of go through that in terms of our plots. So we had said that in this Vx we have this downward curve, but it's not quite able to reach that because it is decreasing to this point. And let me try to line this up with my, so it would be decreasing towards a negative Vp, but when it reaches this point, then our output is going to switch high. So our output comes up here, and then it's going to be at our high state. And we also said that this Vx value, once that output switches high, well now it's charging up back towards Vx. So we have something that looks like this. So I've drawn this kind of poorly. It should be the same time constant for decreasing and increasing. And we also noted that, so this is going towards positive Vp. But once it reaches this value of V gamma, that D1 gets forward biased and it gets clamped at a value of V gamma. So it looks something like this. Okay. So a couple things to notice is, of course, one, we're going to want to calculate the sort of period of this pulse t, and we're also going to want to address this time between our t and t primed and say what exactly does that mean. Okay, so first, I guess let's talk about this t to t primed window. And basically what this is saying is even after our output has returned back to this V peak, we still have to wait for the capacitor to charge up to V gamma before we can see another triggering event. So let me come here and we have to say we have to wait till here So wait until here before triggering again. And so that's, of course, if we want to see sort of our expected behavior. And so what we can do then is we can sort of define this time between t primed and t as our recovery time. So we say this time here is t sub r, which is our recovery time. And so, well, we'll come back to that in a second. So now let's address finding this period t. So if we want to find this period t, let's come down here to a new page. We can say that for time between 0 and capital T, we know that the capacitor voltage equation. So between 0 and capital T, our capacitor voltage is given by our V of x of t is equal to the final value, and again, this is the final value. If nothing were to interrupt the circuit, it would eventually get to negative Vp, plus the initial value, which was where it was clamped at V gamma, minus the final value of negative Vp times e to the minus t over tau, and again, that tau, as I've written a couple times now, is Rx times Cx. So if we want to solve for our period capital T, well, we can say we know at time equals t that our capacitor voltage Vx should be equal to negative beta Vp, because that's the point where the output of our comparator switches from low to high. So if we solve for that, and I'm not going to go through the details, but if you have any questions about it, feel free to let me know. If we solve for that, we get that the duration of that pulse is Rx Cx times the natural log of 1 plus quantity of V gamma over Vp divided by the quantity of 1 minus beta. And again, remember, in this case, beta is our R1 divided by R1 plus R2. So this defines our pulse width. Okay, so a couple assumptions that we can make if we want to sort of have a simpler equation to deal with. Of course, this boxed equation is going to give you the most accurate results, but we can make a couple assumptions to make this easier. So let's say we assume our V peak is much greater than V gamma. Again, whether or not that's reasonable depends on values you're working with. Typical diode cut-in voltages on the order of a volt or less. Peak value might be as much as on the order of 10 volts, so this might be a reasonable approximation. We can also assume that our R1 is equal to R2, and that gives us that beta equals 1/2, the same way we saw in our astable Schmitt trigger oscillator. And so plugging all of that in, what we get is that this pulse width T is approximately equal to 0.693 Rx Cx, and the approximate equation for our recovery time would become 0.405 Rx Cx. So I'm not going to go through it, but we could use sort of a similar approach as to what we did here with our capacitor voltage equation in order to determine an expression for our recovery time T sub r. So that sort of work is shown in the notes on Canvas, and if you have any questions about it, let me know, but I'm just going to go ahead and write our final result here is that this recovery time is equal to tau, which is Rx Cx, times the natural log of beta plus 1 in the numerator, divided by 1 minus V gamma divided by Vp. So that would be the expression for our recovery time. And again, keep in mind for both of these equations, our beta was defined as R1 divided by R1 plus R2. So that does it for our oscillator unit. So next we'll be looking at our high frequency, and then after that our electromagnetic interference.